one molecule in 100 that has a charge on it for typical charge densities in an OFAD. But in these conducting polymers, the charge density is often much higher. It can be up to 1 charge per molecule or 1 charge per repeat unit. And then you need to take these other two factors into account. The electronic charges, they interact with the dopant counterions. There's an attractive Coulomb interaction between the, let's say, the holes on the polymer, if it's p-type dope, and the negative counterions that stabilize that electronic charge. And then you also need to take into account the electron-electron interaction between the carriers. And so that makes it really complicated. And maybe it's fair to say that despite the discovery having made in 1977, maybe the transport physics of conducting polymers is still not fully understood. And then the other reason why this is still an interesting topic, why I'm still talking about it today, is that there is a recent interest in applications that rely on these conducting polymers in bioelectronics. There's been interest in neuromorphic computing. And our interest is mainly driven by applications as thermoelectric materials. So my group has become interested in using organic semiconductors for thermoelectrics. Let me just introduce that application briefly. You might know that we waste a lot of energy in the form of heat. Among the primary energy that's embedded in our energy carriers, we actually only use about 1/3 of that primary energy in useful energy services, and the other 2/3 are just wasted as heat. And I find that quite a shocking fact, and just inefficient processes. And so thermoelectric converters or thermoelectric generators, they take some of that heat and convert it back into useful electricity. And that's not a new idea. I think the interest in organic thermoelectrics probably goes back to these two papers here in 2011. Xavier Crispin and Magnus Berkelind's group in Linköping published that actually PDOT, conducting polymer that many of you will know, is actually quite a decent can be quite a decent thermoelectric material. It has a figure of merit, ZT, I'll explain in a moment what ZT is, of 0.5. The best inorganic thermoelectrics that operate near room temperature, they have a ZT of about 1. So PDOT is coming pretty close to the benchmark inorganic thermoelectrics. So there was a lot of excitement at the time about this discovery. It's maybe fair to say that not much progress has been made since, or that in many respects there has been a lot of progress, but PDOT is still the best organic thermoelectric to date, so people have tried a lot of materials and none of them has beaten PDOT. There's been a lot of progress in, so PDOT of course is a p-type thermoelectric, but n-type thermoelectrics, there has been a lot of progress, and here are some examples of recent polymers that have been demonstrated as n-type thermoelectrics. There's been some work from Jan Hayes' group, Tsar's group, and this is an interesting material that was published two years ago. So the n-type thermoelectrics are now almost as good as PDOT, but overall we don't have a better organic thermoelectric than PDOT. And so why is it so difficult to make good thermoelectric materials? A thermoelectric basically relies on the Seebeck coefficient, and the Seebeck coefficient is a fundamental transport coefficients of metals and semiconductors, where you essentially place your material in between a hot and a cold temperature reservoir. And then in that temperature gradient, the electrons preferentially diffuse from hot to cold. And then they pile up at the cold end and build up a negative potential at the cold end. If you have an n-type material, if you have a p-type material, it's the holes that preferentially diffuse from hot to cold, and then the voltage at the cold end is more positive than the voltage at the hot end. And so that's the Seebeck coefficient. The Seebeck coefficient is essentially measuring how much thermal voltage you generate in a 1 Kelvin temperature difference. And so Seebeck, that thermoelectric voltage, the Seebeck voltage, then if your material is conducting, you can then drive a current, and that's how you convert the heat that generates the temperature gradient into electrical power. And so the ZT figure of merit is essentially dependent on 3 transport coefficients, the Seebeck coefficient S, the electrical conductivity sigma, and the thermal conductivity kappa. You want S and sigma to be as large as possible, and you want kappa to be as small as possible, and that's because a good thermal insulator makes it easier to generate a large temperature difference. If you have a highly thermally conducting material, it's very difficult to build up a large temperature gradient across the active material. And so it's now easy to see why it's so difficult to make good thermoelectrics, because these transport coefficients, they're not independent of each other. So this plot here shows how these individual transport coefficients depend on the carrier concentration. Alpha here is actually, it's a bit confusing, I'm sorry, this alpha is actually S in this. So the Seebeck coefficient here typically decreases with increasing carrier concentration. Of course, the electrical conductivity increases with carrier concentration. So you can't really, you can't simultaneously optimize S and sigma. And also kappa tends to increase with carrier density, because as you make the material more electrically conducting, also its thermal conductivity increases. You all know this. You know that copper, for example, is a good thermal conductor, and yeah, it's very difficult to make good electrical conductors that are thermally insulated. And so what people typically do to optimize their T is to carefully tune the carrier concentration and find the point at which that T is maximized. And that typically gets you into a regime of carrier concentration 10 to the 19, 10 to the 20, maybe 10 to the 21. So the carrier density in these thermoelectrics is really high, and you're really bulk doping the material to carrier densities that approach the limit of 1 charge per pt. And so we got interested in understanding the charge transport in this regime. And the approach that we've taken is, because we are physicists, we actually like to work with model systems. So we've tried to develop, over the last couple of years, my group has tried to develop model systems for thermoelectric polymers and try to understand the physics of these model systems, and then hopefully come up with some design guidelines for developing better thermoelectric material. So we started out by, in order to develop these model systems, we had to have some doping techniques that allow you to dope these materials to well-defined carrier concentrations. And we built on some work that was published a couple of years ago by Jun Takeya's group in Tokyo, and developed this ion exchange doping methods, which is essentially an improvement over the conventional molecular doping. You know, in molecular doping, you have this material. If you want to p-type dope an organic semiconductor, you typically use an electronegative molecular dopant that has an empty molecular orbital, a LUMO level that sits below the HOMO level of the material that you want to dope, and then an electron transfer happens from the polymer onto the molecular dopant, and then that's how you achieve p-type doping. In the ion exchange doping method, we include, for example, here we have a film that we want to dope, and on top of the film we have an electrolyte that contains a molecular dopant as well as an ionic liquid. And then what happens is that the molecular dopant, for example, ferric chloride or so, can be used to then induce the initial electron transfer from the polymer onto the dopant molecule. But then on the surface, basically, the molecular dopant anion gets exchanged with the ionic liquid negative ion. And then what gets incorporated into the organic film is the ionic liquid anion together with the hole that you've generated on the polymer chain. And that's an advantage because the ionic liquid anion is more stable than this radical ion that you would generate in molecular doping. And the other advantage is that you can choose that ionic liquid anion from a wide range of anions. You can basically run through the catalog, order lots of ionic liquids, and then look at, for example, how the conductivity or so depends on the size or shape of your counterion. So one of the model systems that we've looked at in a lot of detail is PBTTT, this thiophene-based conjugated polymer doped with these different ionic liquid anions. So you can see here the microstructure of PB-T. PB-T, as many of you will know, then forms this lamellar microstructure, where essentially parallel to the substrate, you have an alternating layer sequence of conjugated backbones and alkyl side chains. The alkyl side chains, they interdigitate. So it's a beautifully, the undoped system is a beautiful crystalline system with interdigitated side chains. And when you dope the material, essentially what happens is that the interdigitation opens up a little bit, and that defines a little molecular cavity, and you can incorporate the counterions into that molecular cavity. And then you can see a little cartoon here. So this is this cavity here, and the ionic liquid anion fits into this cavity right next to the polymer backbone. And so you can incorporate ions of different size into that cavity, from small anions like PF6 to larger anions like RAF. And so the first thing that we did, and work that we published a couple of years ago, is to investigate how the conductivity of this PB-T depends on the size of the counterion. And so you can see that, actually, sorry, before I discuss it, I want to explain briefly how we determine the doping levels. And so a simple way to determine the doping levels in a system like this is to do XPS. And if you look at the sulfur core level, the polymer PB-T contains sulfur. The dopant, in this case TFSI, contains sulfur. These two sulfur components are chemically shifted in XPS. So you can see one component here due to the dopant counterion, and you can see the other component here is due to the polymer, and then you can determine the ratio between, you can determine essentially how many dopant ions you have per repeat unit of the polymer. And what we find at the highest doping levels in PB-T is that you have a doping concentration of 8 times 10 to the 20 per cubic centimeter, and that essentially corresponds to this structure. You have, in every cavity, you have a molecular dopant sitting. So you have essentially one charge per repeat unit at the highest doping levels. So that's why it's a beautiful model system. It's highly ordered. You have essentially exactly one charge per repeat unit. And so then we looked at how this depends on the size of the anion. You can see that here are some GWAX, grazing incidence, wide X-ray, wide angle X-ray scattering images. And I don't want to discuss them in detail, but what you see essentially is that for all these ions, small to big, the polymer remains highly crystalline. You can see these clear diffractions for the lamellar packing. You can see the pi-stacking diffractions. So the polymer remains crystalline. You can put these many ions in, but the polymer remains highly ordered. And what we thought would happen is that actually we thought we would see the highest conductivities for the largest anions, because we thought a large anion is further away from the polymer backbone. The Coulomb interaction, the Coulomb attraction between the counterion and the electronic charges would be weaker than for a small anion that gets close to the backbone. But that's not what we saw. You can see that here, the conductivity is actually independent of the ion size. For all these ions, we see high conductivities between 800 to 1,000 Siemens per centimeter. So we find that the conductivity is actually independent of the ion size in this system, in this beautiful model system. And then my colleague Ian Jacobs, he then decided to study this in a wider range of polymers and looked at different polymer systems. And it was confirmed, in all of these polymers, we do not see a dependence on ion size. What we do see is a dependence on the degree of crystallinity. We see, for example, that the conductivity depends strongly on the paracrystallinity. Paracrystallinity is a measure of the degree of disorder. So if you want the highest conductivities around 1,000 Siemens per centimeter, you need to have a system like PB-T where the paracrystallinity at the high doping level remains very low. If your system introduces a lot of disorder as you put the ions in, we see much lower conductivity. So what's the reason why our expectation wasn't fulfilled? Why do we not see this strong dependence on ion size? The basic reason is that this is a result from a simulation that shows the electron wave function in a system like this. So the black dots here are the individual repeat units of the polymer. The orange dots are the counterions. And then the green dots are essentially sites on which the electron wave function has a finite amplitude. And what you see is that the electron wave function in these systems remains highly delocalized. It's more delocalized than the distance between the counterions, the orange dots. And that means that the electron wave function is able to average very effectively over that Coulombic landscape that the ions generate. So whether you have a small counterion or a large counterion, the electron is just averaging and smoothing that landscape very effectively, and that's why the conductivity is not dependent on the ion size. So that's the first lesson that we learned by looking at these quantum systems. We then took it a step further more recently and looked at a phase of PBTTT which we call the ribbon phase. And the ribbon phase is essentially it's the same microstructure, it's got this interdigit lamellar microstructure. But on top of that, in the ribbon phase, when you're near PBTTT to temperatures above 180 degrees C or so, it enters a liquid crystalline phase where the polymer chains also adopt some smectic microstructure. So when you then cool down from that high temperature to room temperature, you have a structure where the polymer chains, in addition to having this lamellar microstructure, they also segregate into layers. So this is looking at the film top down. So you can see these individual polymer chains, these individual crystals nicely segregated. And then the chain ends are basically located in these grain boundary regions that occur on a regular periodicity. So this distance here would be the full chain, the extended chain length. Then you have a grain boundary, and then you have another polymer crystal here. And this is what we call the ribbon phase. If you do an AFM microstructure image, or if you're an atomic force micrograph, you see these ribbons, they look like spaghetti running from left to right. And each of these ribbons is a little polymer crystal, and the dark regions in between are those domain boundaries. So every 60 nanometer or so, you have one of those domain boundaries, and then you enter a new polymer crystal. With a blade coating technique, we can align these ribbons. So we have essentially films where we have the polymer chains all aligned in one direction, the ribbons running all from left to right, the polymer chains running from top to bottom. And then we have a very regular structure where you have crystalline domains, the domain boundary, crystalline domains every 60, 70 nanometers. And so in this system, we thought this is a system where the transport, if you measure the electrical conductivity in this direction, so that means along the polymer chain direction, the conductivity is strongly limited by these domain boundaries. Every 60 nanometer, you hit one of those domain boundaries, and then the charge have to hop from one chain to the next within one of those domain boundaries. That's the rate limiting step for the conductivity in a system like this. So we thought, in order to improve the conductivity, we thought, let's try to incorporate some tight chains into this system. And the simple way you can do that is to basically, essentially make a blend, where you make a film with a particular molecular weight, and then you add a small percentage of a polymer that has a slightly higher molecular weight. And then you incorporate what we were hoping, that we would incorporate these red tight chains, the longer molecular weight chains. If we're lucky, they would get incorporated in this way here, where they form tight chains between those crystalline domains. And we were hoping that this would increase the electrical conductivity, because then the charges can move across one of those domain boundaries without having to hop onto another chain. They can move on one chain into the next crystalline domain, and then in the next crystalline domain they can hop onto the next chain. But that's easier, because there you have closed pi-pi stacking, you have an ordered microstructure. It's like a high-speed train station in China. You don't want to get off onto the next train somewhere in the countryside, but you want to get off on the next train at the train station, where it's easy to get onto the next train. Yeah? And this simple idea actually worked beautifully. Sometimes simple ideas don't work out, but this one did. So you can see here the electrical conductivity as a function of the blend ratio. So 0% is just the low molecular weight polymer. 100% is just the high molecular weight polymer. And in between you have different blend ratios. And what you can see is that as we add a small percentage of the higher molecular weight polymer, initially the low molecular weight polymer on its own has a conductivity of 1,500 Siemens per centimeter. And then when we add a little bit of the high molecular weight polymer, the conductivity jumps up to 5,000 Siemens per centimeter. And then if you add too much, it goes down and it settles off at around 3,000 Siemens per centimeter. So that's pretty much exactly what we had expected. As we incorporate these tight chains, we improve the conductivity. We provide pathways for charge transport through these domain boundaries. We were initially hoping to prove that directly, so I was naive enough to ask my students to find ways to measure these tight chains, but unfortunately we haven't succeeded. We haven't got a technique that's able to image a particular tight chain in one of those domain boundaries. It's just very difficult to see these tight chains. So what we did instead is to do a careful microstructural analysis of these different films. So what you can see here is on the left are the AFM images, the XPS measurements, and also the GWAX patterns of just the low molecular weight polymer, just the high molecular weight polymer, and then the optimized blend with the highest conductivity. And what you can see is that in the AFM images, they all form these ribbons. So they all form this ribbon phase. In XPS, you can see that the ratio between the dopant peak and the polymer peak is about the same. So all these systems are doped to 1 charge per repeat unit, so there's no difference in the doping concentration. And if you look at the GWAX, you probably can't see a difference there. So the paracrystallinity in all these polymers remains high. The paracrystalline remains low. 67% is very low value. So essentially, we couldn't see with all of these techniques. We couldn't see like yes, you. Did that make sense? So with none of these techniques, we were able to see any differences.
再动一下电脑就行。长时间不动了。之前可以。
I think the projector switch on.
之前是动一下电脑就可以了。
这个有吧？这个还有吧？
有好了，上来了。
So with none of these techniques, we were able to see a difference. So the polymers have the same charge density, the same microstructure. So we concluded that the only reasonable explanation for this improvement is indeed the hypothesis that we have these tight chains and they do increase in conductivity in the way I explained. So we now have a model system where we can study the thermoelectric physics. So we now have a model system where we can study the thermoelectric physics, and I don't want to discuss it in too much detail because I want to move on to something else. But we've, for example, been able to establish by looking at the temperature dependence of the conductivity and fitting that to a grain boundary model, we've been able to show that indeed, as we incorporate these tight chains, we can improve the grain boundary resistance and reduce the grain boundary resistance. What's interesting here is the thermal conductivity. I want to just highlight that a little bit. So the thermal conductivity as a function of temperature. These data points here are the undoped system. So that's just the lattice thermal conductivity. There's not much difference between the blends and the neat polymers at room temperature in terms of their lattice thermal conductivity. When you dope, of course, the thermal conductivity increases because the electrons, they carry heat, so the electronic contribution to the thermal conductivity is important. There is actually a law that tells you how much the thermal conductivity should increase when you dope. So there's the so-called Wiedemann-Franz law that describes the ratio between the electronic contribution to the thermal conductivity, kappa E, over the electrical conductivity sigma, should be given by a fundamental constant, which is the so-called Lorentz number, which you can express in terms of the Boltzmann constant divided over the electron charge, and then times the temperature. So if this law was valid, we can plug in our electrical conductivity sigma, 5,000 Siemens per centimeter, at the optimum point. Then our electronic contribution to the thermal conductivity should be 3 watts per meter Kelvin. So the total thermal conductivity should be somewhere up here. So the fact that we only see a thermal conductivity of around 1.4, 1.6 means that this Wiedemann-Franz law is not valid in the system. That's good from a thermoelectric perspective, because we don't want the thermal conductivity to be increased much. But we can now study why this is, and because it's such a beautiful model system, we can now study why this might be. So that we're continuing to work on this system, so maybe when I come to you next year, when Pink still wants me, then I can tell you a bit more about that. So it's not yet a great thermoelectric system. In this model system, we get ZT about 0.1 or so now. But it's a credible model system. It's not quite as good as PDOT, but it has a level of performance that allows us to do meaningful investigation of the thermoelectric physics. Okay, now I want to switch gears a little bit and talk about. The projector doesn't like me.
straight.
Yeah. So
Yeah.
switch.
That's a switching.
Can I not directly connect with HDMI? Recovered. So I want to talk a little bit about OECTs. OECTs, organic electrochemical transistors, are very popular these days because they are very good devices for bioelectronics, and people are also interested in them for neuromorphic computing because you can dial very precise conduction states when you basically in an OECT you have a source and a drain, you have a polymer layer, active layer, and then you have an electrolyte and a gate electrode. Sometimes the gate is actually on the side of the device because all you need to do is, well, when you apply a voltage to the gate, the ions in the electrolyte get pushed into the polymer film. So when you apply a negative gate voltage, then the negative ions get pushed away from that gate electrode into the film, and then you can basically, with the gate voltage, you can dial in a particular conduction state. That allows you in neuromorphic computing to define conduction states. For us, it's also we use OECTs just as a tool to study physics, because we basically, if you want to study the phase diagram of the transport properties as a function of carrier concentration, you don't want to make 100 different films and then measure them all to measure the transport concentration. In an OECT, you can really dial in particular conduction state, do your transport measurement as a function of temperature, for example, go to the next gate voltage, dial in a different conductivity, and then you study charge transport as a function of carrier density. And so this is an example, I've talked about PB-T. Here is an PB-T OECT. We make them with an ionic liquid-based electrolyte. PBDF is the scaffold, polymer, and then we mix in the ionic liquid. And you can see here the device structure. This purple region is the active layer of PB-T. It's patterned into this elongated shape, and it's in contact with lots of different electrodes. And we need these electrodes to measure the different transport coefficient, to measure the Seebeck coefficient, to measure the Hall effect, to measure the magnetoresistance, anything that you want to measure, the 4-point conductivity. We can all measure that in this device. And here is one of the transfer characteristics. So as you turn on the device at 0 gate voltage, the channel is not conducting. And then as you turn on the device, it becomes more and more conducting. At the highest gate voltage, you reach a conductivity of about 1,000 Siemens per centimeter. And that's exactly the same state that you reach with the ion exchange doping that I explained previously. One charge per repeat unit, and then you can study the charge transport in the metallic state, the highest conductivity state. And here you see what I mean when I say studying the transport physics. This is dialing this high conductivity state, and then you can measure the conductivity as a function of temperature. It's pretty metallic, so pretty temperature independent. And then at this condition here, if you set this gate voltage, you see a more insulating characteristics where the conductivity drops strongly when you reduce the temperature. Here is the corresponding Seebeck coefficient. It's p-type, so it's pole transport. And as you increase the gate voltage, move towards this highest conductivity state, you can see the Seebeck coefficient drops and reaches values around 15 to 20 microvolt per Kelvin at the highest conductivity and has this characteristic linear temperature. So that's all what you would expect. It's a simple system. This is a system where we've seen a little bit more interesting behavior. This is a DPP-based copolymer with this DPP-BTZ. We've studied that polymer in a lot of detail for OFADs. And here you see a slightly more interesting behavior. Here, the transfer characteristics as you increase the gate voltage, the conductivity first rises, then reaches a peak, and then if you push further, if you put more negative ions in, try to dope it p-type even further, the conductivity drops again, and at the highest gate voltage, you reach an insulating state. And we measure the Seebeck coefficient. Initially in this regime, the regime 1, the blue regime, the Seebeck coefficient is positive and drops as we move towards the peak. And then as we move across the peak into this regime 2, the green regime, the Seebeck coefficient switches sign and becomes negative. So that's interesting. We are actually not the first group having observed this. So this behavior has been seen in other polymers. This is some work from Dan Frisby's group in Minnesota, who's seen similar things in P3HT. So here you see a similar conductivity peak and then an insulating regime at high gate voltage. This is some work from Simone Fabiano's group in Linköping in BBL, an N-type polymer, where you also see that if you push the gate voltage, in this case positive gate voltage, if you push it too far, the polymer becomes insulating. And the reason that the explanation that's been given in these two papers is essentially that this insulating behavior at high gate voltage is a result of the electron-ion interaction. The assumption is that if you push a lot of ions in, eventually the charges will become localized by the attractive interaction with the negative ions, and then at these high ion densities, you have very localized charges that don't conduct very well, and you have an insulating state. That's not the only explanation that's been given. This is some recent work from Alberto Saleo's group, who's shown that actually you also need to think about the microstructure. So if you go to these high doping levels and push beyond the peak in the conductivity, actually they found that in P3HT or in this thiophenes-based polymers, the microstructure actually degrades. The polymer is no longer very crystalline. You actually get a lot of disorder incorporated into the polymer at these high ion densities, and that might be a factor that you need to take into account when you try to explain this conductivity. So we got interested in this problem and looked at a number of the polymers that we've investigated, and this is a polymer that we've looked at a lot in IDTBT. I've spoken about it in previous talks here. It's a very nice FET polymer. And when we investigate it in an OECT, we see this characteristics here. So at 0 gate voltage, you increase the gate voltage initially, the current rises, the conductivity increases up to a peak. If you push further, the conductivity decreases. But if you push even further, at some point, the conductivity rises again. And this hadn't been seen before in a conducting polymer. So this re-entrant metallic regime is a new observation. And this immediately excludes a few possibilities. The two explanations I've given before, that the electron-ion interaction at high ion density localizes the charges, is unlikely to be the reason here, because why would it be that if you push even more ions in, why would the charges suddenly become delocalized again? It's unlikely. Also, the microstructure explanation that I've given is also not likely to work because, again, why would, if this regime is due to the polymer getting more disordered, why would suddenly the polymer become more ordered again as you push even more ions in? It doesn't make sense. So in order to understand what this is, you have to, of course, ask yourself, what's the actual carrier density? And so we went back to our XPS technique and determined at the different operating points along this transfer characteristics, I've reproduced the transfer characteristics again here, determined what the carrier density is. And what we found is that at the peak in the conductivity, this first peak in the conductivity, the carrier density from XPS is exactly 1 charge per repeat unit. What that means is that the homoband is half filled at that point. The homoband has 2 electrons per repeat unit. So if you have 1 charge per repeat unit, the homoband is exactly half filled. If you push further along this curve, at the valley here, at this point, we have about 1.5 charges per repeat unit. And then if you push even further, at the maximum currents here, we get 3 charges per repeat unit. What that means is that the most likely explanation for this behavior is actually a very simple band filling interpretation. So at the peak, we have half of the electrons out of the HOMO have been emptied, so the band is half filled. At the valley, we think we have essentially emptied the entire HOMO level. There's no electrons left in the HOMO level. And then if you push even further, we think we are able to see conduction in the HOMO -1 state. That's the next deeper lying valence band state. And we're starting to introduce holes into the HOMO -1 level and see conduction due to the HOMO -1 level. And that interpretation, that simple band filling interpretation, is in fact consistent with the Seebeck coefficient. So what we see in the Seebeck coefficient, in the regime 1, the first regime where we increase the conductivity towards the peak, we see the p-type Seebeck coefficient decreasing as we approach the peak. At the peak itself, the Seebeck coefficient switches from p to n and becomes negative. And then if we push even further into this regime 3, the Seebeck coefficient jumps again and becomes positive. So we have a p-n-p transition in the Seebeck coefficient. And that's exactly what you would expect with this band filling interpretation, because in this regime 1, you're dominated by holes at the top of the HOMO level. In the regime 2, you are dominated by the remaining electrons at the bottom of the HOMO level. And in regime 3, you are dominated by holes at the top of the HOMO -1 band. So this Seebeck is very consistent with this simple band filling picture. So I want to explain briefly why we can see this in IDTBT and not in the other 2 polymers. The first thing to say is maybe that a general reason why we can see this is that we use this non-aqueous ionic liquids. I mean, if you were doing this with an aqueous electrolyte, this is what you would normally do for a bioelectronics application, you can't really go to these high voltages. I mean, we apply 2, 3, sometimes up to 4 volts to the gate, and with an aqueous electrolyte, you would get, of course, decomposition of water under these conditions. So in the ionic liquids, you can go to these high voltages without decomposing the electrolyte. The reason why we can see this in IDTBT but not in the other polymers has to do with the electronic structure. This is a single chain, very simple DFT calculation of the electronic structure of IDTBT and the other 2 polymers. So what you see here is that in IDTBT, the HOMO band, which we fill initially, is very close to the HOMO -1 band. So once you fill the HOMO level, the HOMO -1 band is easily accessible. In DBP-BTZ, where we enter this insulating regime at high gate voltages, the HOMO -1 band is deeper down, and it's probably too difficult to access the HOMO -1 level. In PBTTT, in principle, the HOMO -1 band should be accessible. It's quite close to the HOMO level. But the problem that we have in PBTTT is that this structure where you have one charge per repeat unit is actually energetically very stable. So you have this interdigitated structure with one charge per repeat unit, and we find it very difficult to push more ions into that structure. We just can't charge PBTTT to higher charge density. IDTBT is quite a disordered polymer, and it's easy and possible to put more than one charge per repeat unit in here. So, and that's, you can see that here, this is an operando GWAX measurement where we actually charge and discharge the polymer and take the GWAX pattern. And if you look carefully, you can see some variations in the GWAX pattern as we charge and discharge, but it's not changing very much. It's quite a disordered polymer, so you cannot see very sharp diffractions. But as you push these ions in and take them out again, the microstructure doesn't change very much. And that's one of the reasons why we can put these so many ions in without really degrading the microstructure. So that's essentially why IDTBT it's possible to see this effect in IDTBT. Okay, and in the last few minutes, I wanted to talk about another experiment that we've been able to do in these OECTs that is a little bit unexpected. So the idea that we had is that we were interested in what's actually the mobility of charges in such a highly doped polymer film. And one way to determine this that we thought would be to make a dual gate device. Because my book is, we love FETs, so we thought, okay, let's put this OECT on top of a silicon oxide wafer with the bottom gate. And then the experiment we were trying to do was to dope the polymer to a particular doping level with the ion gate at the top, freeze the device to low temperatures so that the ions are frozen and can't move anymore, and then start operating the bottom gate and to add a few more holes or take a few holes out, depending whether you take a negative or a positive gate voltage, and then measure how the conduction through that film changes as we operate the bottom gate. So just adding a few more charges and seeing how much the current increases should allow you to determine the mobility of these charges, because we know, of course, with an FET gate, how many charges we introduce, because we know the capacitance of our bottom gate dielectric. So we thought what we would see is, it would be a fairly bad FET because it would have a huge off current, but we thought we would see a small increase of the current towards negative gate voltage, a small decrease towards positive gate voltage, should be linear maybe, and then from the slope we wanted to determine the mobility. We thought it would be a difficult experiment because, well, I mean, even if you make the polymer film very thin, you have so many charges in the bulk, and with the FET gate you just modulate a few. We estimated that you would maybe get 1% change in the current for a 10 nanometer film. So we thought it would be difficult, but worth trying. So here is what we actually saw. So this is the transfer. This is the transfer characteristics that I've already shown you, with the peak in the conductivity, the valley, and then this regime 3 due to HOMO -1 conduction. And in the insets, you see the characteristics of this device when measured at low temperature, where the ions are frozen. And then you see how the current depends on the gate voltage, FET gate voltage, the bottom gate, the voltage applied to the silicon gate. And let's focus maybe on this point here, which is the peak in the conductivity. What we thought we would see, maybe at this point, we should see for both negative and positive gate voltage, we thought we should see a small decrease in the current. Because with the ion gate, if at this point you apply a bit more p-type doping, the current drops. We thought if you apply a negative gate voltage that is also a little bit more p-type doping, the current should drop. The other direction, again, the current should drop as well. But what we actually saw in the experiment is that in both directions the current increases. And not just by 1%, but by up to 12%. At other points, you can get similar current increases. In some cases, you get up to 100%, more than 100% increase in current. So completely unexpected, and it really puzzled us we didn't understand what this was caused by. And I now want to explain to you briefly what we think is happening here, why we get this beautiful ambipolar response at this point, and the current increases by quite a bit more than we had expected. The first thing we did to understand this was to measure the temperature dependence of this effect. And in particular, we were interested how this changes as you go to higher temperatures. And higher temperatures, you can't do this on a dual gate OECT, because if you're operating the bottom gate device at room temperature, the ions are mobile, you would de-dope the film with the FET voltage. So you'd have to do it on a, had to do this experiment on a film without an electrolyte present on the top. So what we did, we doped the polymer by ion exchange doping to a particular doping level, removed the electrolyte, so I have a doped film with a fixed ion concentration, and then we operated the bottom gate. And at room temperature, what we saw is actually what we expected. It's linear, and essentially this nonlinearity that I've shown you is not present at room temperature. But when you cool down the device to below 240 Kelvin, then you start to see this nonlinearity emerging and this ambipolar shape of the transfer characteristic builds up. So it has something to do with a process that happens between room temperature and 240 Kelvin. And what we think is happening there is that the ions are becoming frozen. So there's the polymer glass transition in that temperature regime, there's the melting point of the ionic liquid. And so we did some fluorine NMR. I don't have time to discuss it in detail, but in fluorine NMR you can basically look at the dynamics of the counterion. So the counterion has fluorines, and you can look at how the dynamics of those fluorine counterion changes as a function of temperature. And what we saw is that at around 240 Kelvin, there is a particular motion, basically the fluorine, the dopant counterions stop moving. So they're unable to respond anymore and unable to move in the polymer network. I've tried to illustrate that in a little cartoon in order to make it clearer. So this is our polymer network with maybe some crystalline domains, some disordered regions. These orange sites here are the counterions. The green sites are the counterions. The orange blobs are the counterions. Sorry. The green dots are the counterions. The orange blobs are the electronic charges that we induce when we do. So that's the system that we start with. And now we add an extra hole into that system with a field effect gate. There's no extra ion going in because it's a field effect gating experiment. And so when we do this, so that extra electron goes in, or extra hole goes in. And then what's going to happen? At room temperature, the first thing that's going to happen is that the other electrons, they will feel the presence of that extra hole and they will respond. They're probably moving away because there's a repulsive interaction with the other electrons. And then the counterions will also respond. At least they should, but not on this projector. On this projector they are frozen already. Now they do. So the counterions will also respond at room temperature and will move maybe a bit closer to that extra hole because they're attracted to long directions. At low temperature, my animation is not. This is the same experiment at low temperature. At low temperature, the electrons will still be able to move. They move away from that extra hole, but the counterions are not able to move. And so they stay in place. And we think that as a result of this, the extra charge, I'm sorry. It's responding. As a result of this, the extra charge is able to delocalize more strongly. So that's a simple explanation why we see this increase in current, why these extra electrons are essentially more delocalized than the charges that you induce with the ion gate. It's actually a bit more complicated, and do you have time?
Yeah.
I want to explain a little bit the physics in a bit more detail. So a conducting polymer is essentially a system of localized electrons, where the individual electrons are localized, and they experience disorder. So it's a disordered, localized electron system. And if you think about the electronic structure, you have the electrons interacting by their Coulomb interactions. So this is a little cartoon of maybe the energy level diagram of such a metal, where you have occupied sites, where the electrons are sitting in occupied levels. Then you have a Fermi energy somewhere here, and above that you have empty sites. And if you now think about the electronic structure of a system, imagine that this is the ground state of this system. And now you want to construct an excited state. And the way you can construct an excited state is by taking an electron from an occupied level below the Fermi energy and promote it into an empty level above the Fermi energy. That will cost you an excitation energy, which is given by this energy difference between this level and that level. But you also need to think, because in an interacting electron system, you also have the Coulomb interaction. How do you change the Coulomb interaction between the electrons by this process? A simple way to think about it is that it's essentially an attractive electron-hole interaction. So the electron in this level, once it's occupied, interacts coulombically with an attractive interaction with the hole that is left behind in the original site. And that electron-hole interaction is negative. It stabilizes the state. And if this site is close to the original site in position, then that stabilization can be quite large, because the Coulomb interaction decreases as 1 over r. So if the final site is close to the initial site, that stabilization could be significant. So the total excitation energy is the sum of this energy difference here, plus this stabilization from the electron-hole interaction. And so if the neighboring site is quite close, that could be negative. The sum could be negative. But that can't be, because we are constructing an excited state. This state here, this excited state, needs to have a larger energy than the ground state. What that means is that the next site where this is possible must be quite far away. This attractive interaction needs to be small enough that it doesn't compensate for the single particle excitation energy. And in another way of saying this is that essentially the density of states at the Fermi level needs to be small in a metallic system like this. There can't be a neighboring site where you can make this excitation. The next site needs to be quite far away. And that's another way of saying is that actually the density of states at the Fermi energy is suppressed. And that's the concept of a Coulomb gap. In a metallic system like this, where we have localized electrons under the influence of disorder, you don't just have a smoothly varying density of states with energy, constant density of states or square root of E or whatever you might assume. In addition to that, there is also this suppression of the density of states at the Fermi energy, and that's called the Coulomb gap. That's a feature of these metallic electron systems. The Coulomb gap has an important property, which is that as you change the electron density, it moves with the Fermi level. So if you put more electrons in and shift the Fermi level in this direction, the Coulomb gap moves with it, like this. So if I change the electron density, I would expect that the Coulomb gap remains tied to the Fermi level. So in our experiment, we are moving the electron density when we add extra charges, and this physics alone would mean that we shift the Coulomb gap with the electron density, and not much would change. So this isn't an explanation. This doesn't provide an explanation of what we see. What we would need in order to explain our results would be something like a frozen Coulomb gap, where as you add extra charges in, maybe you can actually move the Fermi energy out of the center of the gap to the sides of that gap. and then you could access states with higher density of states, and that could explain why we see this increase in conductivity as we add more charges and or take some charges out. Yeah? So that was the idea. Can we come up with a mechanism for freezing this Coulomb gap? And so we worked with theoreticians, with Gabriele Davino in Grenoble, who is in Simone Frattini's group, and they developed this model Hamiltonian for a system like this. I've shown the picture before, so you have sites. These black dots are sites. This direction here from left to right is the polymer chain axis. The direction from bottom to top is the pi-pi stacking axis. And then you introduce dopant counterlines. These orange blobs are the dopant counterlines. And then you calculate the electron wave function, you can calculate the conductivity. So it's quite a realistic model of a polymer system. It's carefully parameterized with EFT calculations to make sure that the disorder is taken into account in the correct way. And when they then calculate, they can calculate the density of states. This is just a single band, the HOMO band. And you see that at the Fermi energy, you see these Coulomb gap. You see this depression of the density of states due to the electron-electron interaction. And what's interesting is they've done this calculation under two conditions. The gray line is the condition where you take into account the disorder in the transfer integrals and whatever, and you take into account the electron-electron interaction only. If you take, then you get a Coulomb gap suppression as you see here. If you take the electron-ion interaction into account as well, if you allow the ions to relax a little bit when you change the electron density, then this Coulomb gap becomes deeper. And that makes sense. If you allow ions to relax, that will tend to localize the charges more strongly. And the fact that we see this Coulomb gap deepening is consistent. And so what the simulations show is that they've been able to now do the simulations of the field effect experiment. So you add a few more charges into the system, and you can calculate the density of states under two conditions. In one condition, they allow the ions to relax. That's our room temperature experiment. And in the other condition, they keep the ions frozen. They don't allow the ions to change their positions as you add more electrons into the system. And what you can see here is indeed that under the conditions where the ions are frozen, we can basically move the Fermi energy out of the center of this Coulomb gap. And then you'll be able to probe conduction under the conditions where the Fermi energy is in a region of the density of states where the density of states is higher and where the localization length of the electrons is also larger. And that's the reason why the conductivity, which is the simulated result here, the conductivity is able to increase as you add these extra electrons or take them out with the field effect. So we have a fairly good understanding of what the physics is that's responsible for this unusual field effect response. And it's important for two reasons. The first reason is that it allows us to probe the Coulomb gap. We can understand the formation of this Coulomb gap in these materials. It's obviously quite an important feature of the density of states of these systems. We can also see, I've actually been able to see, the theory predicts that those field effect electrons should be more delocalized, as I've explained with my little cartoon. And we can see that in the spectroscopy. I don't have time to discuss this in detail, but this is charge modulation spectroscopy, where we basically look at changes in the optical properties of the doped film when we add these extra charges with the field effect gate, and we can indeed see that they are more delocalized than the dopant-induced orbs. And finally, I want to just briefly talk about why this is important, or why could this be important. And this is a measurement of the field effect modulation of the Seebeck coefficient. So in this case, we make a doped film, and we measure the Seebeck coefficient of that doped film, and then we look at how much the Seebeck coefficient is modulated when we add a few more electrons or a few more holes into the system with the field effect gate. And you can see that here. at zero gate voltage, where there is no extra holes or extra electrons, we have a Seebeck coefficient of 60 microvolt per Kelvin due to the doped film. If we use a negative gate voltage, minus 50, our Seebeck coefficient increases to 66 microvolts per Kelvin. That doesn't sound very much, but it's actually, if you need to think about it, we're adding only 1% of extra charges at maybe just the interface layer, because it's a field effect experiment. The bulk of the film is still has a Seebeck coefficient of 60.5. So these few extra charges, they're able to boost the Seebeck coefficient by about 10%. If we go in the other direction, the Seebeck coefficient actually goes down. It goes down to 50 microvolts per Kelvin. And that's because the bulk is p-type, the interface becomes n-type, and that the n-type has a negative Seebeck coefficient, the bulk is positive Seebeck coefficient, and they cancel each other to some extent. So that makes sense. So we think that if we were able to do this in the bulk, at the moment we are only able to do this at the interface, if we could add these extra charges in the bulk as well, this might potentially provide a route for significantly enhancing the Seebeck coefficient of conjugated polymers. So that's something we are exploring at the moment, whether this is possible to do something similar in the bulk. So with that, I want to conclude. I hope I've shown you that it's interesting to study polymer model systems for understanding their thermoelectric physics. This ribbon phase DB-T is quite a controlled model system that allows us to study grain boundary limited transport in these systems. The OECT is a powerful platform for studying thermoelectric physics. I've shown you that it allows us to study very high doping levels in some polymer systems where we can see evidence that it's possible to completely empty the valence band and populate holes into the next level down, the HOMO-1 state. For those of you who are familiar with inorganic semiconductors, that would be completely impossible. You can't do this in silicon. If you try to empty the valence band of silicon, the structure will fall apart. But with polymers, it's possible to do that. And then finally, these kind of unusual field effect signatures, these non-equilibrium transport signatures that we've seen under conditions where we add extra electrons, under conditions where the ions are unable to respond, provides us insight into the formation of a Coulomb gap in these materials and potentially a method for enhancing their transport efficiency. And so with that, I want to acknowledge the people who've been involved in this work. So Dion is a very good PhD student who just finished his PhD, and he's worked together with Xinglong Ren and Ian Jacobs, Xinglong Ren is a senior postdoc in my group, and Ian Jacobs is just been appointed to a Royal Society URF position in my group. Gabriele Davino is the theoretician who's done the simulation. Tariq worked with Yao to do the NMR. Lou was involved in the dual gate experiments. And then Wenjin did the work on the tight chain. Wenjin is actually a graduate from Tianjin University. And she did her master's degree in Tianjin. And then the chemists want to acknowledge Martin Heaney's group for the PBTBT, Jake Levy for the DPPBT, Ian McCullough for the IDTBT, and we also have some interesting collaborations with Ditching Jang at ICAS. And with that, thank you so much for your attention.
Thank you very much for your very excellent talk. And deep physics about many of the certificates on the